Hi, I'm Katie Antypas. I'm the Nurse Division Deputy, and I'm happy to be speaking to you today at the HPC User Forum. I'm going to be talking today about the Perlmutter system, which is our new system we're deploying at NERSC, and how we've been preparing applications for that system. So first, let me start and tell a little bit about NERSC. We are the Mission High Performance Computing Facility for the Department of Energy's Office of Science. And so we support thousands of users at our facility and on our systems. And those users are running simulations at the largest scale. And increasingly, we're seeing more and more science communities using NERSC to analyze data from experimental and observational facilities, such as sensors, detectors, light sources, telescopes, you name it. So often we're asked, how are the capabilities that NERSC deploys really unique for science? And there's a couple different things that we often highlight. First is that we really collaborate with computer vendors very early on in the process and collaborate and work closely with them to deploy really advanced technologies at the largest scale. We also provide a really highly customized and high-performing software environment for our users for their science. And then we also are increasingly tightly coupled with these experimental observational facilities within the Department of Energy Office of Science complex. And finally, we have a really advanced set of staff with advanced skills in application performance, system software performance, et cetera, that really lend that expertise to the science teams directly. A little bit more on NERSC by the numbers here. So NERSC has nearly 8,000 users from about 1,700 different institutions. And when you look at the breakdown of our users, I think one thing that's most interesting is that when you count grad students, postdoctoral fellows, and undergraduate students, over 55% of our user base come from students. And so we really take seriously our mission to educate and prepare the next generation of scientists in high-performance computing. About over 60% of our users come from universities, another 30% from DOE labs. And each year, there are approximately 1,800 to 2,000 refereed publications that cite NERSC in their research. So a very broad impact in the computational science community. We can also look at the breakdown of science areas that our users are working in. And on the left, you see a circle chart that shows the science programs by the Office of Science areas. And in that case, you can see basic energy sciences, which includes chemistry and material science, has the largest chunk of time at NERSC. And on the right, you can see how those science areas, or those Office of Science areas, are broken down further into science categories. So at NERSC, we typically deploy systems about every 4 years. So our Edison system retired a year or two ago. Our Cori system is on the floor now and supporting users. And the system I'm going to be talking today is about our Perlmutter system, which we have a few users on it now, and we're looking forward to getting more users on in the next couple of weeks. The system is named after Dr. Saul Perlmutter, and Dr. Perlmutter was the winner of the 2011 Nobel Prize for discovering the accelerating expansion of the universe. I think what is particularly interesting about the way Dr. Perlmutter used high-performance computing systems is that he was really a pioneer of using these systems to analyze experimental data, and really was one of the first teams to do that. So Dr. Perlmutter is still a NERSC user. He's been a NERSC user for a long time, and the login to the system will be saul.nersc.gov. He was very clear he didn't want Perlmutter to be the login in case people got frustrated spelling the last name. So we have honored that. Here's a high-level description of the Perlmutter system. The Perlmutter system is it's coming in 2 phases. And so what I'm going to be talking about today is really the phase 1 system. And it arrived this past spring, and it includes over 1,500 GPU accelerated nodes. And so each one of these nodes includes 4 NVIDIA A100 GPUs. And the system has flash files, all flash file system of 35 petabytes as well. And so we think the combination of these two will really be a great boon to computational science and users running on the system. The second phase will arrive later this winter and is comprised of CPU-only cabinets, and those will be integrated into the system with a network upgrade as well. Here is a little bit more detail on how these systems, how these nodes are built up. I think it's easy to forget just how dense these racks are compared to standard racks. So what makes up a rack, which you see over on the right here, is 64 different compute blades. And on each compute blade, there are 2 GPU nodes, and each of those GPU nodes contains 4 GPUs. So we're talking about the power of one of these systems draws around 300 kilowatts, and compared to a standard rack, which might be more like 30 to 50. And so there's just a huge difference here. And you'll see it more in some future pictures, but because of the density of compute in these systems, we use water cooling to cool it in an efficient way. The full system is made up of 12 GPU racks, and then later this year, as I mentioned, there'll be an addition of 12 CPU racks, and the total power draw of the system will be around 6 megawatts. Here's a little bit more detail on the GPU nodes, in particular, how they compare to the A100s compare to the previous B100 NVIDIA GPU. In addition to a significant increase in the peak flop performance, I think what is also helping our users get good performance out of the system is the increased memory bandwidth and the 40 gigabytes of on-package memory, fast on-package memory. Here are a couple pictures of the Perlmutter system arriving at our facility at Berkeley Lab. I want to give a big kudos to our team that is deploying and integrating these systems. You know, it is a major feat to install and configure these systems for, you know, any high-performance computing center system. But then when you put on top of that a pandemic, social distancing requirements, and in the case of Perlmutter, a new network, a new system software, you know, global supply chain issues, it's been probably the most challenging system that NERSC has ever deployed. Here you can see the final installation, and this is a nice picture over here on the right that just shows the complexity of the cabling and then the water and cooling infrastructure on these systems. Next, I wanted to talk a little bit about how we used high-performance LINPACK to really debug and test the system. The high-performance computing community is pretty familiar with high-performance LINPACK, or as we refer to it as HPL, as a benchmark to measure how fast a system, our fastest supercomputers execute. But in addition, it's actually probably one of the best debugging tools that we have for early testing on the systems. And so, you know, we used high-performance LINPACK to really stabilize the system and find many issues. A number of them were related to networking. We were able to identify network cables that, network switches that were miscabled, fix a network health monitoring tool and bugs in both the network and GPU drivers. We found, in partnership with HP and NVIDIA, a number of bugs in the user software. And so all this stress testing, in addition to giving you a performance number, really helps harden the system. And so, of course, we expect when we're bringing in a new system to find any number of issues. These are first-of-a-kind systems and have never been deployed at this scale. But I think it's something to highlight for the community, just how useful some of these tools can be. When we ran the high-performance LAMMP, this phase 1 system is, and not even in the final configuration, is the 5th fastest in the world. And there's a few other benchmarks. You can see that the Perlmutter system performed well on the HPL AI benchmark, HPCG, and actually I'll highlight in this next slide here, the Green 500 as well. So for the Green 500 run, I think what was really interesting to us is that the Perlmutter system was the most energy efficient system in the top 10. And when you look at the Green 500 numbers, what you can see is that most of the top performing systems are relatively small. And so it's to get a high number or to score high in the Green 500 while also being large and including all of the infrastructure is quite hard. And so we were really happy to see that the system performed so well on this benchmark. The Perlmutter system is going to support a really wide variety of different GPU programming models. We think this is really important because our users, they run not only at NERSC, but at many different supercomputing facilities. And so we're really trying to support users where they are. Some are new coming to GPUs, others have been running on GPUs for a number of years. And so, we're going to support CUDA, CUDA Fortran, OpenACC, OpenMP. I'll talk a little bit more about that. Some higher level programming environments such as Cocos and Raja. And then HIP and DPC++ will provide capability with the exascale systems coming online at the Oak Ridge Leadership Computing Facility and the Argonne Leadership Computing Facility. And in addition, we'll support a lot of data analysis and machine learning frameworks as well, which you can see on the bottom line there. So yeah, I'd like to talk a little bit more about our work with NVIDIA on an OpenMP compiler. So many of our users use OpenMP. They've used it on our Cori system, which is a many-core architecture. And we thought it was really important to give the user community a pathway to moving to GPUs that was a non-proprietary portable programming environment. And this is also because we see AMD GPUs coming online, Intel GPUs coming online, and our user base is going to want to be able to run across these different types of GPUs without having to have different instances or versions for these different systems. And so we have been partnering with NVIDIA on this, created a benchmark suite of the most commonly used OpenMP features by our applications. And what you can see on the graph or the bar chart on the left is that the performance that we're getting from the OpenMP compiler is quite comparable to CUDA, which is very, very good news. Our users are also very interested in the performance of their codes and wouldn't settle for a big performance hit in the name of portability. So next, I want to move on and talk a little bit about the NERSC Exascale Science Application Program. We refer to this as our NESAP program. And this is our program for really preparing the user community and application teams to run on the Perlmutter system. So if you look at this pie chart on the right, this is the breakdown of different codes and the percentage of hours that they use at NERSC. Now, you don't have to recognize all of these code names. But what's interesting to observe here is that although NERSC has 8,000 users and 900 different projects, it's not an even breakdown of those codes. So many codes and applications are used very heavily, and in fact, the top 10 to 15 codes make up nearly 2/3 of the workload. And so our strategy here has been to target some of these widely used application codes and the teams that develop them, and really look for the lessons learned in optimizing applications for the Perlmutter system. And then we can take those lessons learned and share them with the broader community through training, training sessions, documentation, community outreach, etc. So our users applied to this program. It was a few years back in 2018, 2019, I believe. And we reviewed applications, and these teams, when they're accepted into the program, they're given a NERSC staff liaison to partner with. They may have access to a postdoc embedded in their team. And in addition, they'll work closely with our vendor partners, such as NVIDIA and HPE. In the NESAP program, there's about 30 different application teams, and they're broken down, as you can see here, about 14 in simulation category, 9 in data analysis, and another 5 in learning. This chart here shows the different teams, the application teams that are part of NESAP, and then the categories of their work. So you can see the data, learning, applications, and then simulation is broken down into a couple different categories as well. And the acronyms over here on the right just show the corresponding Department of Energy, Office of Science offices for these codes. So I wanted to highlight a couple of application teams that are part of the NESAP program and show the performance optimizations that they have made over the past couple years working as part of the NESAP program. And so the first code I'll highlight here is LAMMP, and this code team had a submission, was recognized as a 2021 Gordon Bell finalist as well. And so I think what's interesting to look at, if you look at the graphic on the right, is the change in performance over time. And it's been a number of, let's say, smaller optimizations in this code that, when added together, have led to nearly 100 times speed up from where this team started. And it's a question that we're often asked, or like, what was there a magic or silver bullet that allowed this code to see such a dramatic speed up? And the answer is typically no. There is not just one particular optimization that increases the performance dramatically, but it's a series of steps. So it's finding the next bottleneck, making a change, doing another profile, or finding another pinch point, making another optimization. And this takes time and expertise and partnership with the vendors in order to see these kinds of code improvements. The next code team I wanted to highlight is DESI. This stands for the Dark Energy Spectroscopic Instrument. So this is a team that is analyzing data for the DESI experiment. What's interesting about this code is that it's an imaging processing code that's implemented in Python. And of course, Python isn't one of the historical HPC programming languages, but it's being increasingly used at NERSC. And so it's very important that Python applications run well. And so again, on the graph on the right, you can see the increase in performance with different optimizations that have been made. And so the blue line shows the performance on the NVIDIA V100 GPU, and then what those same optimizations, the performance increases of those same optimizations on the A100 GPU. And so overall, again, it was a series of 5 or 6 different optimizations that ended up leading to about a 20x increase in application performance. This next code, I thought it was worth highlighting again because it was just such an extreme speed up. This is a called TomoPy, and this is again another Python package. This one is used for tomographic data analysis and image reconstruction. And so going from a CPU node to a GPU node, which required a new implementation on the GPU, resulted in over really a 100x performance speed up. And then finally, I think I have one more application highlight. This highlight comes from an Exabiome team. It's part of one of the ECP applications as well. And this is an application that looks at the assembly of metagenomes. And this has been traditionally a hard computational problem because it requires hash tables and graph traversal, which ends up leading to random access memory patterns that are not really high performing or suitable on the GPUs. So this team, led by work by Muaz, really was creative and was working with the NVIDIA team and ended up using some low-level CUDA intrinsics in order to get a performance implementation. And so for the graphic on the right, you can see in blue the performance of on the CPU versus the GPU, and you can see the very impressive speed up of 7x when you're at 64 nodes. The code does become communication bound as you go to the higher concurrencies. And so there's less of a difference at the highest concurrency. But overall, when this kernel was implemented back into the larger code, there was a performance improvement of about 42%. And this was nominated for a best paper for SC21 this year. So overall, the performance increases that we're seeing across the board throughout the NESAP program have been just really impressive. And this takes a lot of dedication and hard work by the application teams, but really also in partnership with performance engineers and vendor partners. And some of the key takeaways have been that it's really important to expose as much parallelism as possible. And then when you're working on the GPU, really minimizing data motion, especially from the host to the device and back to the device to the host. I think having the larger high bandwidth memory on the GPU does help that as more codes try to stay within that memory domain. Sometimes trying to do that, it does require new algorithms. And so you'll see a lot of our NESAP engineers are helping with algorithmic changes as well. And what we found is that optimizations along these lines really end up helping on all architectures. So if you take that same code and you port it back to the GPU, then you will see performance increases on the CPU as well. But of course, our goal is not to just increase the performance of those codes, those 30 codes that are part of the NESAP program. We also want to take those lessons learned back to the broader community. And as such, we've held a number of hackathons. Of course, these have been quite different in the pandemic era. I mean, we used to get teams together for actually a couple of days. And you get everyone in the same room working really closely, looking over each other's shoulder on a computer screen, and that's not happening now. But instead, we've had these virtual hackathons, and we've broken them up into shorter sessions spread over a number of weeks. And so I think we have found a way to make these successful and collaborative in the COVID era here. So some of these hackathons, they're dedicated for these NESAP teams, but we've also partnered with NVIDIA for some public GPU hackathons, and NERSC has provided mentors. So that because we know that some of all of these codes will end up running on NERSC in the future as well. And then we are also working with the community to make sure that community codes run well on Perlmutter. So sometimes, for example, VASP or Quantum Espresso, these are applications that we at NERSC will install for the user community, and then users will use that executable or those binaries. And so in that case, NERSC works directly with the developers of these community codes to make sure we have a performant implementation or installation on our system. NERSC staff also participate in standards committees, programming models committees, so we can make sure that we're providing feedback that will help the scientific community. And then we also partner with vendors for performance tools, and some of the most important. It's hard to improve the performance of your code if you don't know what your target is, and how much faster your code could go. And so there's a number of tools like the Roofline tool that have been picked up by vendors that can be extremely useful. So with that, we are very much looking forward to enabling NERSC users on Perlmutter as soon as possible, hopefully in the next couple of weeks. And overall, I think NESAP has been really successful in preparing applications, and a significant portion of the NERSC workload for running on Perlmutter. There's certainly still more work to be done, but we are really looking forward to getting users onto the system here as soon as we can. So thank you very much for your time, and I hope you enjoy the rest of the HPC User Forum.